Hey, in this video I'm going to show you how to convert from Cartesian coordinates to spherical coordinates and how to do triple integrals using spherical coordinates. So if we have a point defined by Cartesian coordinates, it has the coordinates x, y, and z, and let me draw projections so that you can see where the point exactly is. So this is the x coordinate, the y coordinate, and the z coordinate. And we want to convert this to spherical coordinates, rho, theta, and phi. So we can say that this point is at a distance rho from the origin. So the distance from the origin to the point is called rho. We say that the angle between the positive z-axis and this radius rho, the angle is phi. And if we find the projection of rho on the xy plane, it's going to be this line over here. Let's call this the radius r. And the angle between the positive x-axis and this radius is theta. So we say like how far the point is from the origin, the angle between the positive z-axis and the radius of the sphere, and the angle between the projection of the radius of the sphere on the xy plane and the x-axis. So that's how we define a point in spherical coordinates. So from this sketch over here, we can say that z is equal to rho cosine phi, and that r is equal to rho sine phi. We also know that x is equal to r cosine theta, y is equal to r sine theta. So if I rewrite this, I can say that x over cosine theta is equal to r, y over sine theta is equal to r. So if I substitute these two equations, this one and this one, into this equation over here, we can say that x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta. So I'll write this here. X is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta. So that's how we can convert from Cartesian coordinates to spherical coordinates. So if we want to compute the triple integral of a function over a region R, of course this is on Cartesian coordinates, and you can go in any order you like dz, dy, dx. We can convert this into spherical coordinates. So it's the same region R. A function, instead of x, we're going to write rho sine phi cosine theta. Instead of y, we're going to have rho sine phi sine theta. And instead of z, we're going to have rho cosine phi. We're going to have a Jacobian that's rho squared sine phi. And then we're going to go d rho, d phi, d theta. I talk about general change of variables and why we have Jacobians in another video, so you can check this out. So I also want to mention that the highest value phi could take is equal to pi. Unlike theta, which can range from 0 to 2 pi, phi can only range between 0 and pi. And the reason is, if you try and create a sphere, like in general how spheres are created is that you have the xyz plane here, you have a semicircle, and this semicircle is rotated around the z-axis for one complete revolution. So you see here the angle phi, which is the angle from the positive z-axis going the clockwise direction. The maximum angle here is pi. You can't go over pi. So that's why phi has to range between 0 and pi. so let's have an example and see how we can integrate using spherical coordinates. Okay, so we want to find the volume of the sphere centered at the origin with radius r. So sketch a sphere. And we know that the volume is equal to triple integral 1 dv over the region E. It's called our region E. And since this is a sphere, it makes sense to use spherical coordinates. So we're gonna have 1 times dv. So first we're gonna need to write the Jacobian, rho squared sine phi, and then d rho, d phi, and d theta. So now we need to set up the limits of the integration. To find the limits of rho, we're gonna start at the origin, go radially outwards, and we see that the sphere is defined at the origin, and that we always exit the region at a value of rho equal to r. So rho is gonna range from 0 to r. Now we need to find the limits of phi. Again, since this is a complete sphere, phi could only range between 0 and pi. And again, because if you try and sketch a sphere, it's a semicircle rotated around the axis, so you get the sphere. And finally, theta, you look at the projection of the shape on the xy plane, you see that this is going to be a circle that's defined in the 4 quadrants centered at the origin, so theta is going to go from 0 to 2 pi. Now the only step remaining is to evaluate this integral. So we're going to integrate rho squared sine phi with respect to rho. So we're going to get rho cubed sine phi divided by the new power, evaluate at 0 and r. So we're going to get r cubed divided by 3 sine phi. It goes from 0 to pi, 0 to 2 pi, r cubed sine phi divided by 3 d phi d theta. Now we integrate this with respect to phi, and we're going to get r cubed divided by 3 times -1 cosine phi, phi evaluate at 0 and pi. So if we take negative r cubed divided by 3 as a common factor, and cosine pi minus cosine 0, that's going to be -1 minus 1, so this becomes -2. Then this negative cancels with this negative, and we get 2r cubed divided by 3. So now we're integrating from 0 to 2 pi, 2r cubed divided by 3 d theta. So this is going to become 2r cubed divided by 3 times 2 pi. Therefore the volume is going to be 4r cubed pi divided by 3. So yeah, that's it. If you have any questions, you can leave them down in the comment section below, and I'll be more than happy to answer them.